to fill in the missing. Thank you, Wenlo. And in order for machine to operate at a similar level, they also need common sense. So what is common sense? Take this example, they boil the water. We as humans share massive background knowledge about water, like water is liquid, water needs to be held in a container. This is a background knowledge beyond the information that is conveyed in the sentence. And the same applies for the action boil or boiled water. Like heat is needed to boil water and burner can provide heat. So this is common sense, which is implicit background knowledge that is shared by nearly all people about everyday matters. But it's extremely challenging for an AI system to possess such knowledge. The amount of background knowledge we shared for this single statement is massive. And the knowledge expands drastically when the number of sentences increase. Not to mention the millions of text and documents we interacted with every day. It's almost impossible to store all this information in one single database. And furthermore, the useful background information in this sentence, like where is the water, what tool is used to boil the water, is unstated. And there are usually multiple correct answers to these questions, like water could be in a kettle, pot, glass, or any kind of container. We could also boil water on a stove or in a microwave. In addition, the likelihood of these answers is different. Intuitively, we would think water is more likely to be in a kettle than glass. And similarly, water is more likely to be boiled on a stove than the microwave. So common sense is also probabilistic. It provides us with a probabilistic assumption instead of definite judgment. This probabilistic nature makes it even harder to represent due to its uncertainty. And moreover, if the statement is modified, in this case, adding the context and added spaghetti, the distribution of the answer change as the sentence change. Now the water is more likely to be in a pot. And if spaghetti is replaced with a chemical item, the answer distribution changed even more. The water now is more likely to be in a beaker, and you're more likely to boil it using a Bunsen burner. So the background knowledge we apply change as the basic statement changes. So common sense is also contextual and extremely flexible, which makes it even harder to build an accurate model for. And furthermore, as you may notice, it's not only applicable in general domain, it's also very important in scientific domains, where common sense becomes domain-specific knowledge shared among domain experts. And the domain knowledge exists in different applications in these high-impact domains, like generating new materials, synthesizing procedure in material science, understanding protein-disease interactions in biomedical, or even making judicial decisions in judicial systems. And take one specific example in material science. The discovery of a novel material with desired property usually starts with some precursor material and followed by a synthesis planning procedure, which is guided by either prior knowledge or the experience of chemists. So in this kind of synthesizing planning event, however, there are usually missing informations. For these actions mentioned in the step, like which container should be, where is the mixture material, and what kind of tools is used to perform these actions. This missing information are domain-specific common sense knowledge, and it's very important to get this missing information correct in order to make the synthesizing procedure more understandable and clear for machines. And specifically in judicial system, it's important also to notice that apart from domain-specific knowledge, there is also human bias. And this bias could come from real-life data, and this real-life data distribution contributes most to both common sense and human bias, and they can be all viewed as the implicit assumption we made on this in these situations. But in this kind of situations, we must be even more careful to ensure that we are filling this implicit assumption correctly by building models that could make fair predictions. So in summary, my research focused on designing models. So this is my research area, common sense. And my research specifically focused on designing models and evaluations for this knowledge, which is important for artificial general intelligence, and it can be applied to high impact to other different domains. Also, we can take into account of human bias by promoting we wanted to promote model fairness. And this is the outline of my today's talk. I will start by talking about this probabilistic model we built for common sense, the training details and different applications, and then move on to the current language model's limitation on common sense, pointing out the current evaluation limitations. And then furthermore, we'll talk about the mitigation we made in order to have a better evaluation for common sense knowledge, the probabilistic evaluation framework. So let's get started with the modeling. As we mentioned before, we need a representation for common sense that can model such knowledge using probabilistic abstractions and the principles. But in NLP, we typically learn a vector representation of words. However, these vectors are not naturally capable of encoding a full joint distribution. They rely on this post hoc normalization over vector dot product scores to encode a specific form of conditional probability. And furthermore, if we look closer to rabbit and mammal, these two words, mammal is a general concept, including lots of small concepts like rabbit. But the vector representation can't capture the generality of the word. And moreover, rabbit is a mammal, but mammal is not rabbit. So the naive score function between vectors like dot product, cosine similarity also cannot capture the asymmetric relationships between these two words. So we develop a representation, probabilistic box embeddings. And this is naturally region-based and could represent the generality of the concept and can represent asymmetric relationships naturally by putting one box inside of another. Like here, we're putting the deer box inside of the hoverable box. And furthermore, we could also represent probability using the volume of the boxes. So to be more precise, boxes are axis-aligned hyperrectangulars. In this picture I showed on the right side, these are all two-dimensional boxes, but in reality, we train boxes up to 300 dimensions. And the volume of boxes is calculated by taking the product of all its edge lengths. And since the edge lengths could not be negative, we'll apply a ReLU function here. And furthermore, the volume could also represent the probability of an item that the box represents, where a single box volume represents the marginal probability and the intersection between two boxes represents the joint probability of two concepts. As a result, one edge in the hierarchical graph could be represented using a conditional probability as 1. And this kind of naturally gave us this interpretation of set of Venn diagram interpretation. How do we learn this representation? We usually use a supervised training, and the training goal is to match the ground truth probability, where we use a loss function like cross entropy loss function. So let's see how the boxes get trained. And in the beginning, they're initialized randomly, and we train them to match the target probability. It can be more unary, joint, or conditionals. And for this specific task I show on the left here, we use conditional probability to enforce the aids of relationship between concepts. We want to represent this hierarchical tree structure depicted on the left here. So the supervision here is conditional probability that equals 1. And then the boxes will try to match the target probability by moving towards each other through gradient descent. But there are training difficulties. And what are the difficulties? As we saw before, the boxes get random initialization, and some of them might be disjoint with each other at the beginning, like deer and mammal, where the goal here is to move the deer box into the mammal box. And let's now see how the conditional probability between deer and mammal loss and gradient changes as we move the deer box into the mammal box manually. So in the beginning, nothing will change because there is no overlap between these two boxes. And as a result, the loss is not changing, there is no gradient flowing, and the predicted probability will remain 0. And only if we start to move the deer box into the mammal box, there is still some changes happening in the loss and gradient values. So an obvious problem is this flat area here. There is no training signal to encourage deer box move into the mammal box, where it gives us the zero gradient that creates a huge training difficulty. And we first noticed this problem and solved it in the smooth version of the hard boxes, where we replace the simple value function in the box volume calculation to its smooth version to a soft plus function. And we also showed that in the paper that this simple replacement is the calculation of an approximation of applying some uncertainty to the box edges, specifically convolution with a normalized Gaussian kernel. However, there are more situations where boxes can be effectively trained. If the current training in the boxes are the blue boxes is inside of the orange one, while the goal is trying to separate them out. As you can see, no matter how we move the blue box inside, there is no gradient change. And naive training would not be able to get out of it. And more generally, whenever this kind of crossing situation happens, no matter how we move the boxes along the direction of the crossing, nothing will change. So then furthermore, last year we proposed even smoother version, another variation of box training, Gumball box, where we take a different smoothing strategy. Instead of smoothing box edges, we smooth the box corners. So here are the densities or the loss functions of different versions of box embedding. The height in this graph represents the probability that a box could be inside of a point could be inside of a box. And as you can see, Gumball box has the smoothest landscape by not only smoothing the edges, but also inside of the box area. And such smoothing makes the loss continuous and the boxes can then get effectively trained. And as you can see, Gumball box is able to escape from the previous stuck situations. Now let's move on to applications. Having mitigated all the training issues for boxes, we experimented with different applications. We started with a hand-constructed ontology of 19 concepts, where each concept has different probabilities, and the edge between these concepts represent the Azar relationship. And this data include unary, joint, and conditional probabilities. They will train this two-dimensional box model on these probabilities, as shown on the right side of the slides. It's a little bit hard to say what is actually happening between these concepts, so let's look at the actual predicted probability. The center one is the ground truth conditional probability, and the left ones are one of the baselines we're trying. On the right ones, we have box embeddings. And the resulting, as we can see, the clear difference between the left one and the right one. The training, the resulting box representations could recover the ground truth probability much more accurately than the baseline. And more quantitatively speaking, we could ask flexible queries of this concept in different forms. For example, we are interested in, just in this content space where we only have 19 concepts, we're interested in what's the probability of deer given X, where in the beginning X is nothing, the probability of deer. And then if it's conditioned on being animal, the probability gets higher. And we could negate the query, like what if it's an animal but not white? The probability get even a little bit higher. And more complicated queries like what if it's an animal and herbivore but not white and not white rabbit? And furthermore, if you say it's not a herbivore, the probability of deer goes back to 0. So this is something that is unique to box embeddings because vectors, we are encoding these joint probabilities all in one single space, where vectors are mostly doing point like pairwise comparisons instead of encoding the full joint distribution. And then furthermore, we moved to real bigger data set. It's still like artificial in the sense it's WordNet because, but it's much bigger than the previous 19 concepts. So this WordNet has about 900,000 edges, and we only train these edges on conditional probabilities. The task here is to check the generalization ability of the model on a binary classification task with edges of 1 to 10 positive negative edge ratio. And here, as we can see, we show that Gumball box performs much better than vector embeddings and all its previous like smooth box or like the hard boxes. But more importantly, all the other geometric inspired embeddings, Punker embedding hyperbolic entailment cones. And then we also use boxes to represent sentence entailment using the image caption dataset that include 45 million sentence pairs. And here the training signal is both unary, joint, and conditionals. The task is to evaluate the model's generalization ability as well. And the evaluation task is to compare the model predicted probability to the ground truth probability by comparing the KL divergence and Pearson correlation. And again, we say Gumball box, both Gumball box and smooth box is performing much more better than the baselines. And we also try boxes on different other tasks, like modeling joint hierarchy, common sense knowledge graph, and the typing and learning boxes unsupervisedly through Word2Box. However, despite the effectiveness and great performance of box embeddings, it is still a shallow representation that is only comparable with simple vector models like Word2Vec. There is no deep structure involved. But the deep models in NLP these days are the dominating models and perform so well on almost all the NLP tasks, which is typically constructed using a multiple layers of transformer network. So now let's turn our head to large language models and ask the question of how well do language models capture common sense, which moves to the second part of my talk, where I'll talk about the limitations of current language model and our systematic analysis result on this. The development of large language models brought huge improvement to the field of NLP. And previous work have shown near or exceed human performance on a wide range of common sense tasks, as shown in between this blue bar and the black bar. Such impressive performance could come from the language model itself or the additional common sense task-specific supervision we provided at the training fine-tuning stage. And if we remove the task-specific supervision for fine-tuning, focus on zero-shot evaluation, we ask the question, will the model performance as impressive? And GPT-3 did such an evaluation on a subset of the dataset. We find the gap is different depending on different data set. But for some of these data sets, the zero-shot performance is either similar or even better compared to the fine-tuned solar results. So this impressive performance really triggers the question, how much common sense do they know, or do they actually have any common sense knowledge at all? And in order to answer this question, we performed this systematic study focused on the language model itself without task-specific supervision and without model parameter update. In other words, zero-shot evaluation. So to start the analysis, we choose 4 multiple choice selection common sense datasets to evaluate the model against a different type of common sense knowledge. And all of this is that are multiple choice QA datasets, because that's the most popular form as of today for the QA tasks in NLP. And in our zero-shot setting, given a question and multiple answer choices, the input to the model is a question and answer choice pair, and the language model will return a score for each answer choice, and the prediction is the one with the maximum score. Where the score function here we used is a token level log probability. The language model we used here is Gopher from DeepMind, because of its excellent performance on zero-shot and few-shot performance at various benchmarks. It's an autoregressive language model that composed of, it's a very big model that composed of 80 transformer layers and have more than, it's trained on more than 2 trillion tokens of data, has about 280 billion parameters, is more than 50 times larger than GPT-3. So the first question we ask is, how is zero-shot performance of Gopher? Here we show the random baseline for all these 4 datasets. And then the darker blue bar showed here is the zero-shot performance. And at first glance, the zero-shot result is surprisingly good compared to random baselines, especially for HoloSwag and Pika. And this too even has a smaller gap to human performance, to the fine-tuned SOTA performance compared to baseline, to the random baseline. And while for the rest 2 datasets, the performance is better, but not great compared to the fine-tuned SOTA results. But we ask a harder question. How much does the performance gain comes only from the answers? We check for a harder answer-only baseline, aiming to check how much of the performance gain only comes from the answers. And in this baseline, we only pass into the answers to the language model and then do the same scoring process as we did before. Intuitively, if the model has no bias, or then the answer-only baseline performance should be similar to random baseline. But as we see here, the result is not as expected. Some of the dataset, especially HoloSwag and Pika, the answer-only performance is much higher compared to random baselines. And the fact that they can successfully predict the correct answers indicate, just by looking at the answers themselves, indicate the high performance in zero-shot. It can be attributed, at least partially, to surface cues rather than a deeper common sense understanding. And on the other hand, the result has also shown the evaluation data had certain bias that the model could pick up on the superficial clues. So we need better common sense evaluation. And the next question is, do larger models learn more common sense? This is the zero-shot performance graph of all datasets across different model sizes. The y as x-axis is the number of parameters for the different model, and the y-axis is the accuracy number on all those different datasets. The black dots represent the model size. We experimented with model size from 44 million to the biggest 280 billion Gopher model with the same training data. And first, we can say that yes, larger model have more common sense as the model size grows, accuracy grows. But then the model, the performance plateaus, especially for the largest 3 model, GPT-3, Gopher, and Megatron tuning. That means if we just blindly training bigger models, will not teach language model common sense. We need something more than that. And then another finding of this work is that large language models, another recent finding of the GPT-3 paper is that few-shot works really well for large models. So we did a systematic evaluation under this setup too. Under this setup, the model is provided with n examples of the downstream task, which is then used as the prefix to the evaluation question. And these examples are randomly picked from the training data. We use the question and the correct answer pair as the sequence to prepend to the evaluation question. So here are the results. These few-shot experiments are the average performance of 5 to 10 times of randomly selecting training examples for each task. And we could say that on both HoloSwag and Pika, we don't observe a substantial improvement from few-shot. However, for social IQA, this few-shot, if we prepend 64 examples from social IQA, they outperform the zero-shot model by more than 7%. And we attribute this to the less natural text of social IQA. We find that Gopher, we also find that because like the model is not so familiar with the task format of this dataset, That's why it could actually learn by reading more examples of the task format. And to verify this, we also find that Gopher has the highest perplexity with predicting social IQ answers compared to the other data sets. So this task-specific examples, the conclusion is that task-specific examples provide information of what exactly expected to the task. So few-shot could be very useful when the task format is less natural for language models. And these are the conclusions from this systematic study. Do large language models have common sense? Yes, but their performance is only slightly better than a stronger baseline. So we always need to do a stronger baseline. And the larger models don't always do perform better on this task, but they plateau, the performance plateaus. And as for few-shot learning, the usefulness of few-shot setting, the usefulness of the few-shot experiments is actually benchmark dependent. So as we said before, we should always compare the model performance with strong baselines and evaluate common sense beyond multiple choice benchmarks, which is what I'm going to talk next. Probabilistic evaluation for common sense. So common sense answers are diverse and probabilistic. That's why we really want to evaluate them rather than go beyond multiple choice selections, especially in these prototypical situations. Like, what do people usually do before they leave the house for work? There is so many answers in here, and which include more common answers like take a shower, brush teeth, or less common answers of saying goodbye or things like that. So we create a data set to capture the properties of these questions. The data set is called ProtoQA. The questions in this data set has multiple correct answers for each question. And they also have a corresponding count or score for each question that could represent the distribution of the answers. In order to evaluate these multiple answers with different scores, we also propose a generative ranking-based evaluation that is able to evaluate multiple choices, multiple correct answers, and reward the model with a correct ranking of the answer list, and also reward the model with a higher coverage of the answer list. So how do we get this data set? Turns out there is an American TV show Family Feud who's doing a very similar job. So we make use of the existing Family Feud questions to construct our training data. We start by scraping the data from the fan website and followed by extensive filtering of the questions to make sure they're not too generic or too gender specific. Essentially, we want to remove the bias in these questions. We ended up with around 9,000 questions with different answers. And here's one example. With one question, each question has multiple answers, and each answer has a corresponding score associated with it. However, for evaluation question, we want to have something different because we don't want the model to just read online and could just script the answers, could just get all the correct answers by reading online. So we did extra human annotation. First, we create new evaluation questions by doing a perturbation from the training questions. Then we change something really simple, do a minimal change to the training questions to get all these evaluation questions, like name something people forget to do to name something people usually do before they leave the house for work. And then we get 100 human answers by making this task a Amazon Mechanical Turk task. But furthermore, we want to cluster this answer strings so the answers referring to the same event could be clustered together. For example, breakfast, ate breakfast, and have breakfast. All those are different expressions of the event having breakfast in the morning. So after clustering, we usually get 6 to 8 clusters, which is similar to the training data. And this is an example of the evaluation data. One big difference between evaluation data and training data is that for evaluation, we actually have all the raw answer strings for each cluster. That means we have 100 answer strings, which makes the generative evaluation, which I'll mention later, possible. So here comes to the evaluation part. We have this generative ranking-based evaluation that is able to evaluate multiple correct answers with all these different characteristics we want the evaluator to have. So given one question, we have the ground truth answer set that is clustered into different answer clusters. Name something that people usually do before they leave the house for work. Here we only show 3 clusters. And we also have model predictions, model predicted answer sets. We use a score function to assign a model prediction to ground truth answer clusters. We experimented with exact match or like embedding-based score functions. For more, you can either refer to the paper or talk to me offline. And we get this score function, this assignment matrix. And in order to let the more probable answer, we receive a higher score. We replace the 0, 1 score by its cluster count, by the size of the ground truth clusters. And then furthermore, we want to make sure that the broader coverage of the answer list will receive a higher score as well. Here we apply this optimal matching where we make sure each predicted answers get assigned to the cluster that could maximize the performance, and that could maximize the performance, the evaluation score. Then each answer string will get assigned to a certain score. With this assigned scores, we then proposed 2 metrics to capture the desired property of the evaluation, where we call here max answer at K and max wrong at K. We try several different baselines, and the one performs the best at the time is the GPT-2 baseline. And for this baseline, we first convert a more natural sentence that would be easier. We convert the questions to a natural sentence that would be easier for GPT-2 to predict. Then we tried both zero shot and fine tuning using our collected dataset, training dataset. And here comes the result. Here, as we can see here, GPT-2 zero shot is not performing great. However, after fine tuning, it performs much more better, but it still have a big gap to human performance. And more recently, the solo result of this dataset is a T5 model, which is like a much bigger model compared to the baseline we tried, but then again, still have a gap to human performance. However, there are limitations to ProtoQA as well. The questions, because we derive the dataset from family feud, it only includes typical prototypical situations. The question format is limited. We want flexible questions. And here, essentially in ProtoQA, we did a human clustering with the ground truth answer clusters, which is time consuming and expensive. Can we do something automatic? And then also, we are not really doing a probabilistic evaluation. We was doing a ranking, a simplified version of the probabilistic evaluation, a ranking evaluation. How can we do a real probabilistic evaluation? So this is the last part of my talk, where we have this new dataset and the new evaluation metric, Commonsense frame completion and its automatic probabilistic evaluation. So going back to the beginning example I had before, they boil the water, and where is the water? It could be in all these multiple places and using all these different kind of tools. We want to create a data set that actually reflect to this, because this kind of implicit information could be actually very useful for all sorts of downstream tasks in NLP, like question answering dialogue systems, or any kind of task that involves language. And in order to create this data set, we will start with a context sentence. Here we only cross out high quality evaluation data because we need a lot of human annotations. And we will start with a context sentence, where here we use a common gen, which is a data set that gets all, it's an image caption data. it's a data set that derived from an image caption data set, where most of the sentences did describe a common sense daily situation. And then we do a semantic parsing. In this case, we did AMR parsing to figure out the missing slots that is the missing slots in this sentence. And then finally, we create some questions or just use the raw missing text, the raw missing slot name to ask Mechanical Turks to do some annotation for our data set. But there are errors in the semantic parsing step. So the result parsing structure sometimes has errors. As a result, we manually filtering some of this generated questions, and we ended up with 101 questions. And here are some examples of the question and also what kind of missing slots we're asking. Arc0, who did the event, what the goal of doing this event, and what kind of tools, where is the event, and what time does this event happen. And the right pie chart roughly showed the distribution of the question types in this 100 questions. So as we mentioned in the beginning, for each of this question, there are multiple correct answers, and so we will collect multiple human responses. But many of these responses refers to actually to the same thing. So we will do a clustering to cluster the similar concept into a single cluster. And then after doing clustering, we could actually form a categorical distribution of different clusters. Then one key question is, how many of the answers are enough to approximate the true human answer distribution? And it turns out this is a classic problem in statistics. And this the Neyman-Pearson lemma actually said, if you just do the calculation of KL divergence between the true distribution and the empirical sampling distribution, how many examples you can be is good enough to approximate the true distribution can be bounded by this equation. So this equation may seem very terrifying, but the key important thing here is the KL divergence between this sample distribution and the ground truth distribution. The probability of that KL greater than some epsilon value is bounded by the right-hand side. So here is where N is the number of samples. This is what we're interested in. And K is the number of categories in the categorical distribution. And the epsilon is the KL error rate. So here we did some approximation by using this amount. We did some calculation. We found that if we just collect about 102 questions, answers from the human distribution by setting the number of categories to approximately 8 to 10 categories. Here we set K to 8 categories. We are able to get an error rate that is less than 0.05. So here are the dataset statistics. We crowdsource this where we have 55 dev questions, 46 test questions, and these are similar to ProtoQA. We have questions and different answers. All this 100 different answers. Now here comes to the evaluation. How did we do the evaluation? We collect a large number of answers from human annotator, and we also have predicted answers from the model. We want to evaluate whether these two answer sets have similar kind of implicit distribution so that we could design a probabilistic evaluation. So we did this by doing clustering. That's how human would do it too. We cluster the ground truth and then we match the model predictions to the ground truth answer clusters. Then we would form two categorical distributions. And finally, we could calculate the KL divergence between the two distributions. So this is the full manual evaluation process where we're given two big answer set clusters. We could first cluster ground truth, match predictions to ground truth, and then calculate the score. How do we do it in the automatic way? In order to do the automatic evaluation, first thing we need to do is to cluster the ground truth answers. So to do this ground truth cluster, we first take all these ground truth answers, make this first embed this discrete word tokens as vectors. And we experimented with different approaches and find that fast text performs the best. After getting all this vector representation, we could do clustering, where here we use different clustering algorithms and find that hierarchical clustering performs the best. And then finally, we have all the clusters that is proposed, that is generated using automatic clustering. We can match the predicted answer, the predicted model predictions to the ground truth answers by using some matching function we used before in ProtoQA. And then now the model predictions could be approximated, could be assigned to the ground truth clusters too. And finally, we have this is the automatic proposed categorical distribution, and we do the same of calculate the scores between the KO scores between these two distributions. But a key question here is, how do you know whether your automatic evaluation is good or not? We need a way to evaluate our automatic metric. We're given a question and a large prediction answers. We have some human annotation that will give us a list of scores for all these predictions. And we have automatic evaluation with different scores for all these different predictions. What we want to do is to calculate the Spearman correlation between those two lists of scores to see how correlated they are. A very good automatic metric should correlate with the human scores annotations pretty well. So we first evaluate the metric on ProtoQA, since there are many available answer sets for each question. But a key question here is, how do we get many answer sets for one question? We could sample from existing answer sets, but the answer sets need to have different quality. In a very bad case, we would have model predictions that predict like answers from all different categories with the same probability, which is a uniform categories. This would be a really bad prediction. So the KL value would be high. And model prediction would be better than the uniform category predictions. And then finally, we have the ground truth prediction, where the KL value is going to be like close to 0 because it's the same distribution. So what we want here is we want something that is, we want all the answer predictions to lie in the middle of the perfect prediction and the worst prediction, the bad predictions. So here we used 3 sampling strategies. Vanilla sample is we just sample from the model prediction. And diverse sample, we sample from a linear combination of ground truth and uniform. And centered sample is where we sample from the linear combination of ground truth, model prediction, and uniforms, but the samples are centered on model predictions. So here we can see the correlation score. If we use human cluster, human matching, in all of the cases, the correlation would be 1, which is, understandable. And if we use clustering of human and matching using like the WordNet matching score function, we would get a lower correlation, but still for the diverse sample case, and both diverse sample and centered sample, we get nearly to 70% of correlation score. But however, for vanilla samples, it's really bad. Why is this so bad? We did some further analysis on this. So the key question here, the key problem here for vanilla sample, we believe, is because the answer sets are not diverse enough. The x-axis are the KO values with human cluster and human matching, and y-axis is the KO with automatic clustering and matching. These are the vanilla samples, while for diverse samples, the answer sets are more diverse, so we can see a clear trend of positive correlation between human KL and the automatic KL. And the same applies for the centered samples. And then furthermore, we evaluate this automatic metric on CFC, the Commonsense frame dataset, where we have a Spearman correlation that is even higher than the ProtoQA data. It's more than 80%, more than 80 correlation score. And in this case, we fixed the automatic evaluator parameters with the best correlation score. We then further on to use this fixed automatic evaluator to evaluate the model performance on CFC. So here is the baseline performance. Same as before, we use GPT-2, zero shot, and few shot, and also fine tuning. And as we can see here from the performance, we have GPT-2 large zero shot, GPT-2 large few shot, adding a few examples that help with the model performance. And we also have the GPT-2 XL model. And as the model size grows, both GPT-2, both zero shot and few shot get a better result. And furthermore, the fine tuning is the best among all of this. However, it still gets a really big gap to human performance. So this is the last part of my talk where I talked about Commonsense frame completion and its probabilistic evaluation, where we have flexible questions and automatic clustering evaluation and probabilistic evaluations. This concludes all the main content of my talk, and where I talked about, we started with probabilistic modeling and language model, like the limitation of current large language model and probabilistic evaluations. How long do I have? Should I wrap up soon?
If you have time, feel free to finish the talk. And for audience, if you have like other schedule at 12, feel free to leave quietly. We have the voice lift on, so please leave quietly. Everything will be heard from Zoom. So yeah, please continue, Lorraine.
Yeah, thank you. So yeah, that's my past work. And going forward, I would want to work more on this, like different natures of the common sense knowledge. We're building probabilistic models, doing analysis on language models, and continuing to develop in probabilistic evaluations for language models. So I won't go into further details of how we, I guess I can say a little bit. So I wanted to continue working on probabilistic box embeddings because its ability on doing abstractions, like as we can see here, we show the ability of box embeddings to represent language concepts and is able to represent the abstraction nature of language and represent probability distribution that is naturally through its volume. Furthermore, its ability to do complicated queries with that is able to do more set theoretical reasoning. And these good properties, we wanted to use this good properties and think of a way to combine this box embeddings with large language models. How can we combine this two? And first of all, box embeddings is able to do better with common sense reasoning because its explainability of like all these operations, common sense operations like conjunction, disjunction, negation is easier to represent in box space than vector space. So we could, if we have a model that is able to do this intuitively, we could interpret the model more easily. And then we should, as I said, we should combine this model with vector models to enforce some kind of structure in large language models. And then furthermore, if we also want to evaluate language models probabilistically of its ability to do common sense evaluation. Currently, the language models are trained using one task, and the evaluation time it's evaluated in one specific task as well. So this makes the training and testing rather brittle. We need to train and evaluate the model in a broader sense, where I believe this implicit common sense evaluation is a universal evaluation because almost all language tasks is dependent on this. And we could start by changing the input sentence of the evaluation data to test the model's robustness, which is actually what I'm currently doing at AI2. And we could also design evaluation focus on phrase or sentence model generation with more complicated questions like how do they boil the water? And we can also combine like with different modalities. As I said, large language, if we just continue growing the size of language models, the model is not going to learn common sense. So can we use different modalities to learn more common sense? A typical example is like here, where you say knife and spoons are together, but we don't usually say it in text. But we can clearly say it. We can clearly infer this knowledge from this picture. So can we make language model and image models combined so that the thing we learned in these models are more grounded in real situations? And then we can also apply this to different domains, which I will skip for this one. And this is what I'm planning to do in the future. And I want to thank you thanks all my collaborators and all my collaborators at UMass, my lab mates, and everyone I worked with during my internships as well. So now I'm happy to take questions. Plus, I will be taking new students starting from 2023 at Pitt. So email me if you're interested. And that's it. Thank you.
All right, thanks for the fantastic talk. We're a bit over time because we started late. I'm not sure if Lorraine have time for questions. Maybe we could do one or two if people have questions. Just feel free to speak up. Oh, yeah, please.
I have a question about training the box embeddings. Do you always need an ontology to train them?
No, you don't. Those are just the typical applications we do, but in the Word2Box paper, which I could share the paper later, we actually train boxes unsupervisedly. You should talk to where Shiv at UMass is still working on follow-ups on that, I think.
Okay, thank you.
Over there, we don't have ontology, we just learn box embeddings from raw corpus.
Okay, thanks.
Yeah, I had a question.
Oh, yeah, go ahead.
Oh, hi, Lorraine. Thanks for the great talk. I had a question about the KL divergence evaluation. So I was wondering how interpretable the numbers are, and like, is there some way to measure statistical significance there, or like, how do you know when you're improving like, how do you know the improvement is good enough?
How do you know the improvement? What do you mean? Like the.
So let's say I develop a new system for the task and I get a very small KL divergence improvement. So how do I know that's significant? Is there a way to do that?
Oh, good question. I guess you can do like the standard significance testing, but we don't actually have we didn't propose a way to like evaluate. It's just like accuracy, right? It's just replace accuracy to KL divergence, and you can do all the other significance testing that you do in the when you report accuracy numbers.
I'll follow up later.
Do we have another question? If not, let's give Lorraine another round of applause. Thank her for the wonderful talk, and we'll see you next week.
Thank you.